Sri Sama to proceed with the welcome address.
Thank you very much, Dr. Rohini. ABM Dr. Ajit Tyagi Saab, President of SAMA, Dr. R.C. Bhatia Saab, Chairman of the Advisory Panel of the Lecture Series, and former ADGM of IMD. Today's distinguished speaker, Dr. Randhir Singh, scientist in the Space Application Center, ISRO at Ahmedabad. Members of the organizing committee, distinguished participants from about 60 countries, ladies and gentlemen, we welcome you on behalf of the South Asian Meteorological Association and Birla Institute of Technology, Besra, India. The total number of registrations for this course as in today is 1804. The lectures are also becoming popular on the YouTube channel of SAMA. The inaugural lecture, for example, of this series has been viewed by about 2,322 people, while the last week's lecture has been viewed by 278 people. These numbers are increasing day by day. We are live on the YouTube, Dr. Rohini, Dr. Vidya?
Yes, sir. Yes.
Oh, okay. Sir. So as there are some new faces and also Dr. Randhir Singh is attending for the first time, so I would like to just brief about the lecture series, which I had mentioned last week also. As you know, this is the 7th lecture of the 20 lecture series. This is a continuation of our efforts on capacity building of the people of this region. Many of you may know that we conducted the first online lecture series on atmospheric physics jointly with the SRM Institute of Science and Technology, Chennai, for 4 months, starting from January to April this year, 2023, in which more than 2,000 people from 48 countries registered for the course. We conducted the second online training on the WRF modeling system jointly with the CDAC, that is the Center for Development of Advanced Computing in India, during 3 to 24 April 2023, with hands-on training on the supercomputing system of CDAC. And that was the most challenging part, because remotely logging into HPC in one country from so many other countries is quite challenging because of the bandwidth problem and many other things issues. Now, this is the third attempt on capacity building, as you know, on satellite meteorology. We have got a distinguished panel of very senior scientists and professors from reputed institutions of this region who are experts in the field. The syllabus of the lecture series has been designed based upon the requirements of the member countries of SAMA. This lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of satellite meteorology and have been already working in the field of climate sciences. This lecture series will continue for 5 months, as you know, 20 weeks started on 2nd of September, and it will continue till 20th of January 2024. As we said earlier, at the end of the lectures, we shall provide certificates to all those participants who will attend at least 75% of the lectures. And also at the end of the lectures, we shall conduct a evaluation test in which the grade certificates will also be given to the participants who will score. Depending upon the score, they will be given outstanding grade or excellent grade, very good, etc. So, as you know, the lectures are also live streamed on the YouTube channel of SAMA. They will also be available afterwards on the YouTube for those who could not attend the course live. We shall try to have more interactions between the speaker and the participants in this lecture series. Please write your questions in the chat box. Our moderators will pick up the questions at the end of the lecture, and they will be answered by the speaker. So enjoy the lecture and have a good time. Thank you, Dr. Rohini.
Thank you, sir. Now I invite AVM Professor Dr. Ajit Tyagi, sir, President SAMA, to give the presidential address.
Thank you, Rohini, and very good afternoon, and apologies for my delay in joining the webinar. Bhatia Sahab, chairman of this very important training program on satellite meteorology, which is going on as brought out by Somesh, Dr. Someshwar Das, Secretary Sama, and members of the management committee. This is the 7th lecture and started with the inaugural session where Dr. Kelkar DGM and Dr. Rajkumar Sharma, Director NRSC, and eminent scientists from SEC gave their overviews about the satellite meteorology and space application in space-based satellites. And thereafter, we started with fundamentals of remote sensing and gradually building up. Last lecture was on RGB, where multispectral, how do we use it in our applicational part. And today's lecture series is being a part of this, is a step further, where a very eminent scientist, Dr. Randhir Singh, will be delivering the lecture on application of various products which satellite derive. He has vast experience, both that derivation of various products from the satellite data and also the assimilation of this data in the numerical models. He had been very, very hands-on, I think, satellite meteorology and NWP modeler, a great asset for both meteorological satellite met community and the NWP community. I had been following his progress at SEC, and he had many awards of his work, including the award from the India Met Society, and also a number of awards from the various ISRO programs. So thank you so much, Dr. Randhir Singh. We are really thankful to entire spectrum of senior practicing meteorologists from the SEC, from India Met Department, NRSC, IRS, and of course, Bhatia Sahab is there to support everything. So I'm really happy that this program is going on very well. It's being, I think, response for both online lectures and YouTube is overwhelming. And what we find is the question answer session also is very, very interesting. So it shows the involvement of participants and their interest in learning. So that's, please keep it on. I've been requesting to our distinguished speakers that even after the question answer session, if the participants have, they may approach you. So please mentor them, guide them. And this is the idea of the SAMA, that how do we, young researchers and students, how do we support them online, remote way, because not all institutions have access to advanced developments in these areas. So this is what this lecture series is providing. So let's make best use of it. Once again, my compliments to management committee for continuing with this series of lectures, doing in an excellent manner. And of course, special thanks goes to the resource persons who come and deliver on valuable inputs to the participants. Thank you.
Thank you, sir. So now I request Dr. Polomi Chakravarti to please introduce our speaker, today's speaker. Over to you.
Good afternoon, everyone. I hope you can see my screen over here.
Yeah.
It is my privilege to invite and say a welcome address to Dr. Randhir Singh, who is the scientist SG at the Space Application Center, Ahmedabad, ISRO. He is an expert in developing mathematical models for assimilating Indian satellite radiances into weather prediction models, and his vast areas of interest include data assimilation, radiative transfer modeling, GNS meteorology, geophysical parameter retrievals, and regional climate modeling. He has also significantly contributed to advancing remote sensing data assimilation technique for bolstering numerical weather prediction system. He joined as a scientist at the Indian Space Research Organization, Ahmedabad in 2001 and has since been serving with distinction. He undertook the role of a visiting scientist at NCEP NOAA at Maryland, USA in 2006. In his other international collaborations include his expertise at the Data Assimilation Research Center at the University of Reading, UK during 2008 and 9. Now, he has been presented with several accolades and recognitions. Some of them are, he has been presented with the ISRO Team Excellence Award in 2008. And in the same year, he has also been honored with the ISRO Young Scientist Award. Also, he has been twice recipient of the Boy Scout Fellowship by the Department of Science and Technology, India in 2007 and 2008. Awarded the IMS Young Scientist Award for the best paper on tropical meteorology in 2015. Apart from this, his educational journey has moved from, he has done his MSc from Kurukshetra University in 1997, and he has obtained his PhD in physics from Gujarat University, Ahmedabad in 2005. Please join me in extending a warm welcome to Dr. Randhir Singh as he shares his deep knowledge and invaluable experiences in the realm of satellite meteorology with us today. We welcome you, sir.
Thank you, Dr. Punomi. I request now Dr. Randhir sir to please share his screen and we can start his lecture. Over to you, sir.
Yeah, hi. Could you see my screen?
Yes, yes, sir.
Yeah. Thank you for this nice introductions. So, dear Bhatia ji, Tyagi ji, and Someshwar Das ji, and other panelists, as well as the participant, a good afternoon. And thank you, Sama, for giving me this opportunity to deliver this talk. For these participants. So I will start this talk, and I hope that my voice is audible.
Yes.
Yeah, thank you. So I will start. This is my outline of my talk. I will start basics like weather and climate system. Then I will talk about the physical basis of the satellite meteorology, where I will talk about different platform, orbits, different sensor and channels that are used for the meteorological applications. Then I will move on the retrieval of the different parameters with different algorithms. And then I will talk about the use of these observation in weather and climate models. And finally, I will talk about what are the outstanding issues in weather and climate model. So if you see, and what is the challenge, if you see our Earth system science. So the current challenge is actually to understand the present weather and climate systems and their interactions. And then not only the current, then actually we have to project also what's going to happen in the future. So that is our biggest challenge if you talk about weather and climate system. So if you see what are different interaction or different of this climate system. So there are a lot of feedback if you want to understand how our climate and weather system behaves. So we have to understand and take care of all these different nonlinear feedbacks, like physical, chemical, and biological processes and their observation as well as modeling. Right? So if you see today, what is IPCC 6? Latest reports. If you see the how our global warming and then extreme weather events are increasing. So if you take different scenarios, like what's going to happen if 2-degree warming or under 3-degree warming, or at current level it's about 1.5 or 1.2-degree warming. What is going to happen to different weather systems? So temperature and the drought, precipitation, snow, and tropical cyclone. So how their frequency and intensity will be increasing in different scenarios. So if you take a simple case of, like, say, tropical cyclone. So if you increase the temperature of something like 1.5, so the tropical cyclone intensity will be about 10% higher than what is currently observed. So similarly, if increasing about 4 degrees, which is most of the climate model, if you see the projection actually varies from 1.5 to 4 because of their different climate sensitivity. So tropical cyclone in a very extreme cases, they can be intense as about 30% more than what actually we are experiencing now. Similarly, we have precipitation events. So there will be again like 1.5 times to 2.7 times more intense, as well as in both frequency as well as their rainfall intensity. Right? And this is what actually we have observed from the, like, if you see all the observational data sets, you can see this warming signal is actually observed in all kind of your sphere, like biosphere, chromosphere, and atmosphere. Okay, so if you see the CO2 concentration, then you see the glacier mass, then you have ocean heat content. So you can see that all actually we are getting a very extreme cases, and even we have warming is slightly less if you talk about Indian region or Asian region, but if you see the higher latitudes, warming is much larger. It ranges from about 0.5 to 4 degrees. This is again because of the different feedback in our climate system. So warming is uneven. So in order to understand and model all these interaction and to forecast our future weather and climate pattern, so what we need is we need to understand all these interaction as well as their observations. So this is what weather and climate, how actually it derives. So you can see that basically our weather actually is due to the uneven heating of your solar radiations, and then we have different heterogeneous surface like your topography, water bodies. Then they can modulate this large scale atmospheric circulation, which is actually governed by this meridional gradient of the temperature. And then this local land surface changes and land water distribution, and this will again actually add up all this feedback mechanism. So that's a very complex systems, and to understand that we again need the observations. So how we are actually modeling this weather and climate system? So this is basically mathematical modeling is done basically using all Navier-Stokes equations, where we have all mathematical this conservation of mass, momentum, and energy. You take a simple moisture equation and how we are solving into the computer. This is just you discretize it, and then you'll see that basically weather is an initial value problem. So it is very clear from here that if you want to forecast at a certain time, then you must know what is the initial value of that particular variable. So this is initial value, and then this is the forecast, and this is again governed by your advection and other your processing your models like your advection, convections, and stuff like this. On the other hand, when you talk about climate, so climate is basically a boundary value problems. When you talk about initial and boundary value problems, so what are those boundaries? So boundaries here, we are talking about like what is the solar constant? What are the land use, land cover type? What will be the vegetation scenarios? Okay? And what will be the chemical stage of the your atmosphere? So these different chemical composition as well as the solar radiation, how much solar radiation you will be get in future, what will be the land surface condition, all those what we are calling the boundary condition. Like similarly on the sea surface temperatures, that is also a boundary condition. So when you talk about the climate prediction, then what we need is the boundary values. That is what we have to specify perfectly what will be the boundary conditions. Whereas the weather is basically an initial value problem. We need an initial state of the atmosphere to forecast the weather. Right? So in addition to the initial states, we also must know what is the actually boundary, like what are the land use, what are the vegetation, how agriculture is changing, what are the urbanization scenarios. All those things also we have to take into account when we talk about the climate prediction and climate projection. So this is one simple case when we say that weather is an initial value problem. So you take a very, very simple nonlinear equations like we have in our weather prediction system, like this hydrodynamic equation. So you take a very simple nonlinear equation and just initialize it with some different, slightly different values. Here, in case, if you take a slightly different, like third decimal place, and you see the solution of this equation with 3 initial value. So you can say that after 10 days, I mean, the solution become completely out of phase. So that's how much is our system shows the nonlinearity of the system, and that's what exactly is happening in weather forecast. Okay, so that's why the initial value actually is very critical, because small error with the initial condition can create your large uncertainty in the forecast. Whereas in boundary, initial value doesn't matter. What we want to actually specify is the boundary values. Okay, so that both problems are actually completely different. So what are the observations actually need to understand this climate and weather prediction systems? So we need basically temperature, pressure, wind, water vapor, and atmospheric gases. aerosols, and land surface characterization. Generally, we don't actually talk about much about land surface characterization when we talk about weather prediction. We generally talk about like meteorological, variable. But land surface, when nowadays your model are becoming higher and higher in resolution, both in space and time. So land surface heterogeneity actually plays a critical role, like for example, in your thunderstorm formation, as well as in other rainfall processes, or land surface interaction become very, very important. So we have to take care about this vegetation, land use type also, very high resolution and also the current state of the land surface features, like urbanizations or the agriculture practice, how it changes with time. So all those things we must take into account when we formulate a numerical weather prediction and a climate system. So this is the conventional setup of these observations we are getting from this radio sonde, ship buoys, and automatic weather stations, right? And these observations actually, when we talk about for weather predictions or climate scales, they are actually have a large, representativeness error, because when you talk about weather predictions and climate scales, what we are talking about is a grid average value, like 5-kilometer resolutions or 10-kilometer, whatever resolutions you are having of in your model. But these in situ observation actually represent a very specific point measurements. So we have to take care of all that representativeness error when we actually insert into numerical weather prediction system. And these observations, though they are very accurate and very useful for validation as well as calibration of our modeling system, but when we use into our numerical weather prediction system, we must take care of this, the representativeness error as well as the uncertainty about this mismatch between the spatial scale. So if you see the coverage, if the most important observation, if you talk about, is the radio sonde, because it provides a three-dimensional view of this atmosphere. So, but total number, if you count, there are only about 600 to 700 if you see the global distribution of these observations. Though we have surface observations, they are quite large, but they are only available at only the near surface. Right? Then we have some aircraft observation, and then buoy, that is our oceanic surface. So you can see that there's a large sparsity in the data, and which may not be good for this year high resolution climate and weather prediction system. So that is where the use of satellite observation become very critical. So the advantage of satellite observation is, one is the coverage, and the second is the repeativity, and then representativeness. Because when you talk about satellite observation, they are also similar like what we want to use in weather prediction system. Like they are, the grid average value. Because satellites or whatever sensor you talk, it has, field of view. That is like, it's a field of view, maybe something like 1 to 2 kilometer or 5 kilometer, depending upon the sensor resolution. So that it means that they are more compatible with your weather and climate modeling system. Like there also we need average value of a particular spatial average. So that is again provided by this satellite and remote sensing technology. And then so the representativeness error will become much smaller when you want to use the satellite observation in weather and climate forecasting system compared to the in situ observation. Though in situ observation, as you can say, they are more accurate maybe, but they are more like a point observation. And then satellite again can provide excellent coverage within a short span of time. Maybe every 6 hours now you can get the global coverage of all these meteorological parameters. So first meteorological satellite, if you see, that was launched in 1960s, and it was a very simple infrared and a visible camera. We took a photograph, and then this photograph were merged. Like in this image, if you see that, something like 450 photographs were merged to see that global weather pattern. It was the first time that was actually, realized that weather is a global. It's not you cannot talk weather like a very local. So you have to, when you talk about weather and climate systems, so they are global in nature. And that is very well, you can see from this cloud imagery, how that they are, they are continuous movement of, like, if you see the wave nature of the cloud in extratropical region. So that was the first time it was realized that you need a global coverage when you talk about weather prediction or a climate modeling system. So after that, after 1960s, now we have arrived with a simple, infrared and a visible photograph. Now we have hyperspectral kind of instrument where you have something like 10,000s of channels, which can provide you the very detailed information of the atmosphere, as well as our land surface, as well as atmospheric parameter. So we are having now hyperspectral imaging capability from the geostationary platform. If you see the weight wise, we started with a very, very small kind of a satellites, And now we are launching a satellite of something like 6-ton kind of satellite. So that is how, satellite weight is increasing with the time. And these are the different orbits and different observing system from the space. So currently we are having about something like 160 meteorological satellites and providing about something like 80 million of observation per day. And if you see the total weather and climate systems, about 80 to 90% of the data which is being used in all these weather and climate models actually basically coming from the space-based observing system, whether it's a radar, a space-based radar, or active or passive. I mean, there are different kind of sensors that provide the useful information for. And this is a typical coverage for, if you say LEO satellite, that is basically a low Earth orbit satellite, around something 500 to 600 kilometers. And every 6 hours, you will get this kind of coverage. So every 6 hours, you can almost observe the globe, okay? And different meteorological parameters, okay? And this is from the geo platform. So geo platform, you can get every 10 to 15 minutes, something like 1/3 of a globe. One geostationary satellite can provide information about 1/3 of a globe. So you need basically 3 satellites, 3 geo satellites to cover the entire globe. So we have currently, we have 2 satellites from INSAT 3DR and INSAT 3D from India. And then we have GOES East and West. Then we have from European, that is UMETSAT. And we have from China, FY. And then we have from Japan, that is Himawari. So we have now LEO satellite as well as GEO. So GEO has got advantage that you can continuously, monitor the weather, like every 10 to 15 minutes, you can get the observation of cloud and related meteorological parameters. And what actually we get from these satellites? So we don't get actually directly whatever, like we don't get the temperature or moisture or wind from these satellite. Basically, what we actually get is the radiance or the reflected signal from the satellite, whether it is in radio signal or from the infrared or from the visible. So these you have to convert into the useful meteorological parameter. So this technique again can be active or passive. That is, active means that is the sensor actually transmit the signal, and then scattered signal will again received by this onboard your receiver. Wherein passive, you use the naturally available your energy, whether it's from the sun or emitted from the Earth's surface. And these energy spectra, which actually we are exploring, actually ranges from the visible to the radio waves. So it has a wide range. That again depends on the what kind of application actually we are looking from this remote sensing platform. So we have imager and we have sounder. So imager basically is used to actually, when we are talking about the 2-dimensional field, when we are interested in the, when we have spatial variabilities more, so we generally use the imager. So imager basically provides the high resolution imagery, 2-dimensional field of let's say water vapor or sea surface temperature. Whereas sounder are basically, they are sounding the atmosphere. That is, you get a 3-dimensional view, that is vertical profile of different meteorological variables. That's what we call as the sounding. Then we have radars. Radar is basically what we have like an active sensor. So radar basically work in a microwave. So where both signal that transmit and receive. Then similarly LiDAR, and then GNSS. GNSS is again a very useful technology. Generally, it is used for the navigation purpose, but recently the GNSS technology is proving very useful in the meteorological application. That I will see, and when we'll see the detail about this. So remote sensing, already I might have some lecture. It's very basic. That is generally what we are trying is we are observing the visible, microwave, and infrared. So basically what we are getting is either reflected from the clouds, or reflected from the surface, or reflected from the atmosphere, like for example aerosols. In microwave, again, we can get the reflected as well as the transmitted signal, and infrared basically emitted by the Earth's surface. So all these, depending upon the sensor, the characteristics, you will get the different portion of this radiation. So we are exploring scattering, absorption, emission. And only the GNSS-RO is a one technique where we actually talk about the refraction. So most of this technique, this remote sensing is based on the scattering, absorption, and emission, except GNSS-RO, which generally, which is working on the basis principle of the refraction. Okay, where we are talking about the refraction of the wave. Okay, traveling in from one rare media to the denser media. So that is again the scattering generally have, like when your wavelength is much smaller, like in visible and near infrared, So we'll get the scattering. And this scattering again is basically from the clear sky. If you talk, that is the molecular scattering. Then we have a mean scattering, but basically from fog and the aerosol particle. And the non-selective scattering is when there's a cloud. So basically you won't get anything from the below the cloud. So if there's a cloud and you are getting a observation from infrared or visible, so you are not getting anything below the cloud. Most of the information you'll get from the top of the cloud because they cannot penetrate the cloud. Whereas in microwave, you can actually penetrate the cloud. Okay, so you get the observation even below the cloud. So that is the advantage of the microwave. So, and these are the different, if you want to see how actually the remote sensing is being done. So this is the reflectance signal for different type of surfaces, like water. If you see how the reflected signal, what is the reflectance percentage? So water reflecting much less, okay? And if you see the soil, it is reflecting something like 30 to 40%. And green vegetation actually has, different reflectance at different wavelength. So based upon these, actually you can identify the targets using the visible channels. That is, which is the portion of the cloud and where is the land and where is the ocean, which is the vegetation. All those things actually have been done using the visible and near infrared remote sensing. Whereas when you talk about the pure meteorological sensor, they are generally operated in the infrared band. Okay? Because most of the meteorological sensors are actually based on the emission criteria. That is, what is the radiation, how much is absorbed and how much is get emitted. So these are basic atmospheric spectra. If you see, this is a visible spectra, that is sun spectra. That is how much radiation is coming from the sun and what is the distribution. So most of the radiation we are getting in something like visible band. Whereas in Earth spectra, if you see, the Earth is radiating most of the energy around 10 to 50 and 10 to 12 micron. So this is the Earth spectra. Okay. So this is the different absorption band of different gases. So if you can see that the water vapor absorption band is around something like about 10 micron, and there are some individual band in between. Okay. Similarly, carbon dioxide band are around 15 micron, and then we have around 3 to 4 micron. So similarly, these are different band of different gases, and that is what actually is the basis of the remote sensing. So if you are trying to, for example, find out what is the water vapor profile in the atmosphere, so we have to put our sensor somewhere in the water vapor absorption band. Okay? That is around, for example, in this case, you can say this is around 6 to 7 micron meter. Okay. Similarly, if you want to derive the temperature profile, so temperature profile, generally what we derive is from the oxygen band, that is around 15 micron meter. Okay. So that is the basis of the remote sensing sensor definition and the channel selection. So these are the common band which are used for the meteorological application. So that is the CO2 band, 15 micron. Okay, that is most of the sensor, whether it is on Indian satellite or whether it is on the UMET satellite. So you will find the sensor operating around 15 micron. Okay. Similarly, there is ozone. This is around 9.6 micron. So this band is used to exploit the ozone profiles or ozone concentration. Then we have water vapor absorption band around 6.4 center. That is center of the band, and then this is a wing of the absorption band. So this is again short wave 4.2 for the temperature measurement, and this is the microwave. So microwave, we have a band around 22 gigahertz for the water vapor absorption, and then 50 gigahertz for the temperature. Okay, these are again defined based upon our molecular spectroscopy. If you do the spectroscopy and analyze the different absorption and emission characteristics of different gases. Okay. So then these band are actually defined basis on that this molecular spectra. These are another water vapor absorption, and where we can actually get the water vapor profile using this 183 gigahertz this microwave band. Okay. And the band which are actually in a clean window, that's what we call the surface sensing channel, where we don't have any absorption. That is, whatever energy is emitted by the surface can reach up to the satellite sensor. That's what we call is the surface or window channels. So for example, we have a window channel here at something like 10 micron. So this is a window channel here. So most of the sensor like operating like sea surface temperature or land surface temperature. So you will get a clear signal from this kind of band, which are quite transparent. Okay, so these are called the surface sensing or window channel band. So this again just frequencies. Mentioned the individual value of this frequency, most commonly used for this imaging as well as sounding sensor bands. So this is for the visible and infrared. So visible band is generally used for the cloud feature as well as your surface vegetation characteristics. Then your cloud microphysics, you can use this around SWIR, near infrared and SWIR bands. Then your atmospheric moisture, again 6.5. This is again for the cloud surface and temperature. This is a window, okay? So window means whatever photon you emit that emitted by Earth's surface will directly reach to the satellite. And again, these are all again basically in the clear sky condition, okay? Assuming that atmosphere is actually clear. So once there is a cloud or water vapor burden is very high, then these actually this information what is reaching to the satellite is basically not reaching from the surface. It will actually contaminated by the atmospheric water vapor or the clouds, right? So what I have already mentioned actually basically is the clear sky condition. And these are the for microwave, okay? So like water vapor absorption band, very well known, around 22 gigahertz to 30 gigahertz, 50 gigahertz temperature, right? And these are for the window in the microwave that is generally used for the sea surface temperature and sea surface wind speed measurement over the oceanic region. These are land surface monitoring, which are like vegetation as well as snow cover, land surface temperature, and aerosol. These are basically used for the Earth environmental satellites. That is for EOS. Now we have, when you talk about meteorological satellite, we generally talk about imager and sounder. So imager actually is used for the like when you are interested in the to study the horizontal gradient in some variable like water vapor or cloud imagery, then we are more interested in the imagers. These imagers generally have a very high horizontal resolution, but provide information at a single level, maybe like sea surface temperature or a cloud cover. And when you talk about sounder, then you have a very high vertical resolution and a multiple level. You'll get the information like temperature or water vapor or I mean different trace gases, right? So, and there is a concept of called weighting function. Like if you have, like for example, inside 3D, we have 18 channel sounder and 6 channel imager. So if you see these 18 channel, there are different frequencies, right? So we started from like, this is 650 wave number. So this is around carbon band, that is around 15 micron meter. So these are temperature sensing bands here. And you can see that these band actually, this is the brightness temperature. Okay, as we go up in the troposphere, temperature decreases. So lower temperature means that this particular channel is peaking at higher in the atmosphere. So this is the spectra. So you can say this different channel actually peaking at different height in the atmosphere. Okay. So how to decide that which channel is peaking at what height? So radiation basically received in a satellite channel is coming from which level of the atmosphere is actually defined by the called weighting function. Okay. So this weighting function is actually a derivative of the transmittance. So if you calculate the transmittance using that your molecular database and you calculate the transmittance of each wavelength. So you calculate transmittance from surface to the top of the atmosphere, right? And then you actually take a gradient in the vertical, that is that will give you the sensitivity of this radiance. Okay. So for example, if you have, let's say, a absorption band, this particular absorption band, 15 micron, so that is the center of the band. Okay. So center of the band means that everything is actually reaching to the satellite is only from the top of the atmosphere. So surface to top of the atmosphere transmittance is 0. So it means that nothing is reaching from the surface. And as you go away from the absorption center of that band, you will get information slightly from the below. And if you go slightly more toward the wing of the band, you will get something, everything from the surface. So that is the 0 transmittance mean everything is reaching from the top of the atmosphere. And 1 mean transmittance 1 mean that your atmosphere is quite transparent. So whatever is emitted from the surface will reach to the satellite. So that is how a sounder is defined, right? So you defined a different channel starting from the center of the band, particular absorption band, and go towards the wing of the band. And then this, if you see that in a weighting function, you can see here this weighting function of these 3 channel. So the weighting function is peaking around something like 100 millibar. So this will give the maximum information from the 100 millibar. And another channel which is peaking slightly lower, something like 850. This will give the maximum information in the 850. And another is peaking at the surface, green one. So that means that this particular channel, you will get the maximum information from the surface. So that is how actually the sounding instrument is defined. And this this actually is in a clear sky condition, right? So if you increase the water vapor in the atmosphere, so these will shift upward. This weighting function will shift slightly upward, and then you may get the information slightly from the different level. Okay, like for example, tropical region or mid latitude region where water vapor is very less, you may get information in a particular channel, something like from this channel, maybe slightly from the below near the surface. Okay, because water vapor is less there, and that weighting function will shift downward. Okay, so like that, this weighting function is a very important concept which is used in the sounding. Ideally, we need a something like delta function. Okay, that is maximum at a one particular height and zero everywhere. But in nature, actually, that is never happened. So we generally get some kind of a Gaussian weighting function. So we get a contribution in a particular channel from different layer in the atmosphere with a maximum contribution, but in a certain layer. Okay, so you can never say that this particular information is coming from a 850 millibar. It's never possible. You will get something like it is averaged at a certain depth with a maximum contribution coming from 850 millibar, something like that. Okay, so that is how the sounding instrument actually works. Now we have very advanced sounder like ERC or AIRS, where you have channel like something like 8,000 to 9,000 channels. So that the purpose of this high resolution is basically to get more information in the vertical. Okay, like for example, these are the weighting function of ERC. Okay, that is infrared atmospheric sounding instrument from METOP, where you can see the weighting function are there very closed and they are very narrow. Okay, but still they are not like delta function. Still you'll get the weightage average kind of a information. Okay. And how this information actually we are retrieving from the major radiances or radio signal is, you see that how this a photon emitted by, let's say for example at the surface, is interacting with another layer in the atmosphere, then again re-emitted from that particular layer based upon its layer temperature, so it downward and upward. So like that, each photon actually is interacting with the entire atmosphere and then finally it's reaching to the satellite, right? So if atmosphere is quite transparent, then some photon may directly reach to the satellite. Okay, otherwise most of the photon actually will interact with the upper atmosphere and then finally reach to the satellite. So you have to solve this, what you call the radio transfer equation. So this is a very simple radio transfer equation where I have neglected the scattering. Okay, because when I am considering that there is no rain, then scattering actually can be neglected in infrared region. So this is basically a radio transfer equation where this is a surface contribution, where we need the Planck function and the emissivity, surface temperature. And this is the atmospheric term, where you are taking care of this emission and absorption and emission. And this is the reflectance. That is, if emissivity is not, or surface is not perfectly black body, then you have to take this reflection of this from the atmosphere toward the surface. So basically, when you are talking about the estimation of the meteorological parameter from this satellite radiances, we are actually inverting this equation. Okay, these are temperature and this transmittance. Okay, rate of change of transmittance with pressure. That's what I call is the weighting function. Okay, so this transmittance basically is a function of different gases in the atmosphere, like water vapor, ozone, or different trace gases. So if your channel is sensitive to the trace gases, then you have to take the trace gases also. Otherwise, most of the channel for meteorological purpose, they are mostly sensitive to the ozone, water vapor, and the water vapor and ozone most of the time, right? So whatever based upon your channel characteristics, the transmittance you have to calculate. Okay. So in the retrieval problem, what we are having, we get the radiances here. This is what we get from the satellite. Radiance in different wavelengths or different frequencies. And our aim actually is to get the temperature. This is the temperature here, or the concentration of the different gases. For example, trace gases or water vapor. So that again will be used. Can be formulated using this transmittance. Okay. So this transmittance is a function of concentration of different gases. So you have to invert this equation. If you know this, then we have to get this temperature and this trace gases as well as emissivity also. If you don't know emissivity, then emissivity also you have to retrieve it from the radiances measurement. So that is basically what you call is the ill-posed problem. Okay, because we are knowing only at a selected number of channels and selected number of levels, and we want to retrieve a continuous function. So that's basically underdetermined problem. So how it is being done is there are two approaches. One is what we call empirical regression, where what we do is we take the in situ observation and co-locate with the satellite radiances. And then like other like neural network or machine learning, what you can do is you can get some kind of weight or regression coefficients between the temperature, moisture, or radiances, right? But then for that, you need to actually establish a large simultaneous database for the satellite radiances and then your physical parameters. Then we have another approach, what we call is the physical retrieval using radiative transfer calculations. In that, as I mentioned earlier, is what we call is the theoretical modeling. That is, we have basically, we take a first guess of the meteorological variable, that is temperature, pressure, or different gases. We simulate the radiances using this radiative transfer equation. And then we actually try to invert this. That is, the invert actually is not possible because it's a very complicated equation. So we actually get the approximate solution using a numerical methods. Okay, that I will touch upon when in subsequent slides. That our basic aim here is we get the radiances from the satellites, and then we take a first gas meteorological profile and we try to actually simulate the radiances using this radiative transfer equation, and then compare the simulated radiances with the observed radiances, and then we try to actually minimize the misfit. Okay. So these are the different variables which are available currently being retrieved from different meteorological satellites. So these are starting from, like, say, atmosphere wind, atmosphere moisture, temperature, sea surface temperature, clouds, that is top of the atmospheric fluxes like outgoing long wave radiation flux, rainfall, aerosol, hydrometeor like cloud liquid water, or your ice, snowpack, or this gropal, or all these hydrometeor profile, atmospheric gases like trace gases. Then we have land surface temperature, snow cover, soil moisture, and vegetation. So these are most of the variables generally I'm talking about, which are generally used in meteorological or NWP system. But I'm not touching upon, there are other variables like for physical or biological oceanography parameter like your sea salinity and the primary productivity products. There are other large product coming for the oceanographical applications, which I'm not talking here. So the first variable when you talk about from the satellite meteorology actually is a clouds. Okay, clouds they are visible and they actually indicate this active weather condition. So cloud generally, how to detect cloud in meteorological this sensor from these channels is basically done using threshold technique. Most of the algorithms are based on thresholds or like clustering technique. So you have a signal from different channels, like visible channel, we have infrared and water vapor absorption. Okay, so we have radiances or reflectance coming from different channel. Then if you remember that clouds actually are reflecting more than the, let's say, ocean water or the vegetation. So you can clearly see that if you plot the reflectance, you can see the water is quite dark. Okay, because water has got less reflectance than the your clouds or vegetation. Similarly, if you see that the thick and shallow cloud or your thin cloud or thick cloud again can be actually distinguished based upon the reflectance. So higher the reflectance, mean thicker the clouds. Okay? So like that, we have different techniques using this hyperspectral, this multispectral technique to identify the different type of clouds, whether it's a low cloud, mid cloud, thick cloud, or thin cloud, whether it's ice cloud or it's a cloud liquid cloud. So you can actually identify it based upon these different channels. Similarly, the infrared based on infrared is based on the emission. So emission is basically characterized by the temperature. So if temperature is cold, that means your signal is coming from the much higher in the atmosphere. Basically, clouds are much higher than your surface, right? So cloud will always be colder than your surface. So the temperature is less in infrared channel, means it may be a like clouds, okay? Or it may be a higher cloud if the temperature is very, very low. So depending upon the temperature or cloud top temperature, you can identify whether it's a low level cloud or high level cloud or mid level cloud. Okay. So using all these infrared and visible channels, so you can actually identify the cloud amount as well as cloud classification. And in recent years, nowadays, we have more advanced, channels like near infrared and SWIR channels, which were not earlier used to actually study the cloud microphysics. So you can also identify the different cloud microphysics processes And then you can use these cloud types and their microphysical properties to actually validate your climate and weather prediction models. Otherwise, we don't have, global, without satellite, you cannot have a global cloud data sets and their, microphysical properties. So this is one example here that the model actually used to project this future climate projections are actually validated using the MODIS cloud cover. So you can see these are the cloud simulated by the a climate model. This is in winter and this is in summer. So you can see these are difference here from the actual observed cloud cover. So this is a model simulated minus MODIS observed cloud cover. Okay? This is in winter and this is in summer. So you can see there's a large biases actually in your model simulated cloud cover. Basically, it is negative. So actually model is underestimating the cloud cover. So that's actually having a big issue in most of this climate model. Actually, they are not representing this cloud processes well. And if you can't simulate a cloud, I mean, all your projection, the future projections will actually not be that accurate. So that is one of the application of this cloud cover in validating your cloud processes or cloud microphysics in your weather and climate model. Then we have rain. Okay, so rain can again be estimated using different techniques. So we have visible, infrared, microwave technique. So visible basically depends on the cloud thickness. That if reflectance is more, then you are having high clouds. So there is a chance of having more high precipitation. Similarly, you have infrared techniques where we actually talk about the cloud brightness temperature. So if cloud brightness temperature is less, that means this cloud is actually higher in the atmosphere, which may have some kind of like ice in the cloud. So it may have a high chance of getting high precipitation. Similarly, microwave. Okay, microwave actually has advantage over both infrared and visible because microwave can directly interact with the cloud microphysics. Okay, because microwave can penetrate through the clouds. So it has a direct interaction with the cloud particle. So microwave rain actually is more accurate than infrared and visible. But the microwave has one disadvantage because it has got a poor spatial resolution. The microwave has less energy. So the signal strength will be less and the noise will be slightly higher compared to the visible and infrared. So the spatial resolution as well as the accuracy of microwave-based precipitation may be slightly less compared to the infrared. But it can directly provide you the hydrometeors and the rainfall, actual microphysical processes happening in the cloud. And these are the different channels which are used for the estimation of rainfall in microwave and infrared. Okay. And this is the one comparison between the model simulated and then these satellite-based rainfall. Again, you can see, I mean, there's a large differences between the model which are actually being used for the climate projection. And you can see how Indian region, if you see the Asian monsoon, I mean, there are large differences. So basically, the Indian summer monsoon is strongly underestimated here, or the region where, we have this monsoon trough. And it's strongly overestimated over the Indo-Pacific region where you have this high cloud and large convective system. So again, it's possible to identify using this satellite-derived rainfall. Then we have another important parameter is called outgoing wave radiations. That is the total energy which is emitted from the Earth's atmosphere to the space. So that's what we call is the outgoing long wave radiation. And it's basically the starting from like 2 micron to 100 micron. That is total radiation. Okay. Entire spectrum. If you integrate in azimuth and total these directions, that is what we call the outgoing long wave radiation. So basically, it is measured from an instrument called CERS, that is Cloud and Earth Radiation System, which is having a channel something like 4 to 100 micron. Okay, but generally we don't have this sensor on all the satellites. So what we do is we establish a relationship between your narrow band and the broadband. So we have a narrow band in most of the satellites. You will get the sea surface temperature or land surface temperature, a window channel that is 10.5 micron to 12.5 micron. So that is somewhere here. So we can actually regress or we can fit an empirical relation between the broadband radiances and then this narrow band radiances to get the OLR. So that is generally most of the time this narrow band to broadband conversion is used to get the OLR because this is available only or the limited sensors like MODIS or I think Aqua, I think it's available. Right? So this is now one example how this again OLR can be used to validate your model. Right? So you can again see that there's large differences between your model simulated OLR and then your actual satellite observed OLR. and these are the differences. This OLR can also be used actually to get your to see the climate change, that is your warming signature. This is actually top of the atmosphere. If it's the 2005 to 2019, this is the temporal variation of the net radiation. That is at the top of the atmosphere, how much radiation is coming from the sun and how much is leaving the Earth atmosphere system. So if you take the difference of this, so difference is actually positive. Okay, and it's increasing with the time. What it suggests is that our Earth atmospheric system is getting warmer because your outgoing wave radiation are decreasing. It means more radiation actually is getting absorbed in Earth atmospheric system. So that's again a warming signal, indirectly what you can infer from the OLR and the incoming solar radiation. If you take the difference of this, then you will get this positive difference. Then we have again land surface temperature and sea surface temperature. You can get it from the window channels. As I told you, the window channels are the channel where we are interested to get the surface information. Okay, and surface information we get from the, again, I told that is 10.6 and 12.6 channel. And that is again where water vapor is less. Okay, as water vapor increases in the atmosphere, you have to take the water vapor information to actually get the sea surface temperature or land surface temperature. Otherwise, signal, if you just take this band and if you don't correct for the water vapor, so then you will be underestimating the land surface or sea surface temperature. That's why actually what generally we do is we use a split window technique, where one channel is actually a more sensitive to the water vapor and another channel is less sensitive to the water vapor. So if you take the difference of these, that difference along with the sea surface temperature measuring channel, that is 10.6, we can correct for the water vapor. And that is actually shown here. If you see the transmittance here, this is the transmittance of surface channel. Okay, so you can see the transmittance of surface channel if the water vapor is very small in the atmosphere. So you can see the transmittance is 1 from the surface itself. So what it means that everything emitted from the surface can reach to the satellite. But as you increase the water vapor in the atmosphere, you can see the surface transmittance is decreases. That is surface to top of the atmospheric transmittances. So it's become now 0.6. It means that only 0.6% of the information emitted from the surface is reaching to the satellites, right? And if you further increase it, it's become even smaller. Okay, like in tropical region, we have more water vapor. So the surface channel alone may not give the information of the sea surface temperature or land surface temperature. So you have to correct it for the water vapor information, and that again can be corrected using sensitivity to the water vapor. That's where we use this what you call split window technique. Okay, generally to compute the sea surface temperature or land surface temperature, and that is again a use of this sea surface temperature or the surface air temperature to actually validate your model. So this again, you can see the large biases and these are the state of the art. I mean, the recent climate model which are used in CMIP 5 and 6 to actually test their the validity. These are another wind, which are important parameter used for the NWP system as well as climate. So wind basically are not sensitive to like absorption or this emission spectra, but wind are estimated based upon the cloud movement as well as the water vapor gradient. So from geostationary satellite, we can get the image every 30 minutes or 15 minutes. And what we do is we actually track the cloud movement. So you take a cloud at a particular time and then actually track this cloud to the next after 30 minutes or 15 minutes, whatever temporal resolution you are having. So use how the cloud is moving. So in 2 images, if you can track the same cloud using the correlation pattern, so you can estimate the wind speed. And the height of the wind vector is quite difficult here to assign. And this height is basically assigned using the ancillary data, what we call is the numerical weather prediction model first guess. Profile of temperature, moisture, wind, and we calculate the using radio transfer model the brightness temperature. So using that model brightness temperature and then this NWP simulated brightness temperature, we can actually assign the height of the clouds, and that height of the cloud actually indicate the height of the wind vector. So that is slightly a head hoc kind of thing using both model as well as the satellite observation. So height is very challenging here. If you have something like large vertical shear in the wind, and there are large chances of having more error in the height assignment. But if your shear is small, then height may, assignment of height may not be a big factor. Okay. Similarly, water vapor image is the water vapor channel, which actually peaking is something mid atmosphere, middle troposphere. You can see the large, advection features in water vapor images. So most of the water vapor actually get advected by the wind flow. So if you can track the water vapor gradient, so using that water vapor gradient, actually we can estimate the wind vector. Okay. So this is from basically from the geostationary satellite. Now we have another technique called the Doppler wind lidar. Okay, that is the state of the art and very advanced technique, where we use this lidar measurement in around 400 to 500 nanometer, where a pulse actually is transmitted from a laser, and then because of this particle movement in the air, we get the scattered power, which will have a shift in the frequency because of the Doppler phenomena. So that frequency shift actually we can translate into the wind speed, and it can provide the three-dimensional structure of the wind field. So that is the state-of-the-art latest technology, which was launched by European Space Agency. Then we have a sea surface wind we can retrieve from the scatterometer, which is basically a active radar. We send the pulse in the Ka band and C band, and we get the scattered power based upon the ocean surface roughness. The scattered power can be related to the ocean surface winds. And another recent addition here is the microwave, this radiometry and reflectometry. So reflectometry again is actually basically GNSS technology used for navigation, but recently it has also been used to get the wind speed over the oceanic surface. So here basically what we do is we actually transmit a GPS signal, and that GPS signal reflected from the ocean surface actually received by a receiver here. That is what we call a small satellite. And the reflected power again can be correlated with the wind speed. So this is a technique where we can get a wind speed also in a very severe weather like cyclonic storm, which is otherwise not possible from a standard radiometry or scatterometer, because once there is a heavy rainfall, then scatterometer signal gets saturated. Okay. But in GNSS reflectometry, because it's operate in a much lower frequency, is around something like 1.4 gigahertz. Okay, so that rain attenuation will not be there, and you can get the signal even in the very extreme weather events. And this is one of the a case where it has been shown that assimilation of the GNSS reflectometry actually improved the cyclone intensity as well as cyclone structure. So that is the recent development in the retrieval of the wind from the microwave radio, this microwave instrument, and being used in weather prediction system. Now this is the sounding again. When we talk about the imager, okay, from imager, because we are deriving a single parameter like OLR, sea surface temperature, or cloud cover. Okay, there we are not talking about the multiple level information. But when we talk about sounding, here what is the problem here? We are getting signal from, let's say, n number of channel, let's say 100 channel, or at most, let's say 800 channel something. Okay, or for that matter, let's say for our InSat 3D kind of satellite, we have only 20 channels. So from 20 channels, these are, let's say, for example, weighting function for some channel like 15 channel, I think here for AMSU-A. So from this 20 channel, can we reconstruct a temperature profile? Because temperature is a continuous function of space, of height. So can we construct, infinite number of point using just 20 observation? Okay. So that's basically what we call is an ill-posed problem. So we are actually trying to get a continuous function from a discrete value. That is a ill-posed problem, and that is what exactly happening when you talk about sounding. So sounding here is what we get is this X is a state vector, that is temperature, moisture, or trace gases, and Y is a radiance in n number of channel. So we are trying to get X from Y, okay, and X is a continuous function where Y is only a limited number of observation. So that actually is not possible without taking some first guess. Okay, if you take purely only satellite observation, we cannot invert it. Okay, because there may be n number of solution, and this solution may be different. There will be there may be n number of profile which can produce same radiance, right? So, but then this solution should be unique. Okay, so that is the where when we talk about sounding, we have to take some kind of first guess in order to actually solve this problem. Okay, so when we try to retrieve the vertical profile of temperature and moisture, what we do is we take a first guess of temperature, moisture, or trace gases from numerical weather prediction. Okay, that is co-located in space and time with the satellite observed radiances. And using the radiative transfer equation, we simulate the radiances. Okay. That radiances of a particular channel we simulate from the radiative transfer model and model profiles. Okay, and then we compare the measured radiances which are provided by the satellites, and we compare the their values. So naturally there will be differences, and those differences has to be minimized, right? So this is what we call is a minimization or optimization algorithm here, which I won't go into detail because it's highly technical. So this is a minimization algorithm. So what we try to do is we try to minimize these differences, and how to minimize those differences are basically is a mathematical problem where we talk about this Jacobian and adjoint operator. Okay, so that slightly I will explain, but more technical I want to go. So doing that process iteratively, what we will change this profile. Okay, this model profile will change by some delta x or delta whatever you said, temperature, delta, moisture, and again we'll calculate the radiances, and then again we measure with the observed radiances. Okay, we again compare the differences, right? So we'll do it iteratively till we are actually within that noise level. Okay, till we reach that level where the differences are within that signal, that instrument noise. So that process actually is what we call is the retrieval process, and that is being used to retrieve the temperature and moisture information using the sounding channels. Okay, this is one very simple example I'm giving. These are the, let's say, observed radiances for, let's say, water vapor 6.2 micron meter. And this is the model simulated radiancy. That is what we have taken is we have taken the first gas profile from the numerical weather prediction system, that is temperature, moisture, cloud, liquid water, and stuff like this. And using the radiative transfer model, okay, we simulated the radiancies. Right. This is the channel 6.2, and this is a land. This is a surface channel that is 11 micron. That is surface sensing channel. Okay, near surface. So now we'll compute the differences. If you see the differences between this and this, so the differences, if you, I have not shown here differences because they are absolute value. So if you plot the differences, there will be large differences here. Something like 2 to 3. I mean, if you talk in brightness, temperature. Now we have to minimize those differences, right? So what we'll do is we'll change the model profile like this, and we'll again compute this first gas radiances, right? And we'll again compare with the observed radiances, right? Now how we'll do that? So this is what, as I told earlier, is Jacobian. Okay. So which variable, how at what level and how much I have to change. So if my sensor or my channel is sensitive to the water vapor more than temperature, and this weighting function will help me to to decide at which level I have to change this. So for example, this is a channel number, water vapor channel peaking at something 400 millibar. Okay. So what I will do is I have to change maximum water vapor, or let's say my moisture, around this level. Okay, to impact the model radiances. Okay. Similarly, if I'm talking about surface channel, let's say this is the surface channel whose weighting function is peaking at the surface, right? So I will be changing my surface temperature more to actually impact this first gas radiances, right? So this is basically what we call Jacobian. Okay, this is nothing but rate, that is if you take the first derivative of your radiative transfer model with state vectors. Okay, so that will decide which parameter and what level you have to change, and how much also, that magnitude also you will get from that Jacobian. Okay, so like that, once we are satisfied that differences become very small, that final state vector will become our the retrieved information. Okay, that is how, whether it's a temperature or moisture, or it's a cloud, liquid water, or hydrometeor, that is the same process being adopted. Okay. If you are talking about hydrometeor, we have to take the cloud, liquid water, rain, and ice water also along with the temperature and moisture profile. And also we have to take scattering also, because if you are taking a very simple approach where we are neglecting the scattering, means we are talking about only the clear sky condition. When there is a scattering like cloud or rainfall, then you have to take into account the entire scattering of the radiative transfer equation, and then you have to solve a very complicated equation of this phase function and stuff like that. So it will become very, very complicated when you talk about the cloudy condition or rainfall situations. Okay. This is another example where we talk about the hydrometeor, like this inside 3D observed, for example, a tropical cyclone. This is cyclone Fallin, and this is the model simulated radiances here. So what we have taken is, we have taken the, let's say, model simulated temperature, moisture, and the hydrometeor plus radio transfer model, and we can simulate the radiances, okay, for a particular sensor based upon the sensor frequency and sensor response function. And this is the actual observed radiances from, let's say, sensor of INSAT 3D. Now, if you take the differences of this, right, and you want to minimize that difference in order to improve the state vector, right? So we again start same way, like you take a first gas profile here and then simulate the radiances, compare the difference, and you minimize those differences. How you will minimize is, you have to change this first gas, right, with certain amount of delta X, delta T, or delta Q. So that is again an iterative process. And finally, once you are satisfied with the differences, then final state vector will be the retrieved temperature, moisture, and hydrometeor profiles. That is how things are done. Then we have another very advanced technical GPS radio occultation technique, where the technique is used, what we call is the refraction base. Okay, that is, you have a GNSS satellite here, and we have a receiver here on the LEO satellite. So basically, what happened is that GNSS satellite transmits a signal, and it received at the LEO satellite, right? So as it travels from vacuum to the atmosphere, it get refracted, because it's moving from a denser to the rare to denser media. Law of refraction, that is Snell's law. Now, if you have a exact location of these satellites, both LEO and GEO, as well as we know the distance between this, that is, we know the position of this satellite, exact position of this, and also this, and we know the time difference, that is the straight line also we know, and then curved path also we can calculate, because we have an atomic clock here, right, on this satellite and this set. So we can exactly calculate what is the straight line and from this to this satellite, and what is the actual path traveled by this signal, right? So the difference between the actual straight path and then this electrical path will give the information about the atmospheric temperature and moisture information. That's what we call the refraction-based measurements. And that temperature and moisture actually is related with the refractivity measurement. Okay, this is the relation here. So if you get the bending, okay, so without atmosphere, this ray will pass straight, and with atmosphere in the way, it will bend because of the refraction. So that bending angle actually we can get based upon this measurement of this atomic clock at this satellite and this satellite, right? So basically we get the bending angle. From the bending angle we get the refractivity, and from refractivity we get the temperature and moisture information. And this technique is actually all-weather capability, because it's again operate at something like 1.4 gigahertz, which is insensitive to the rainfall and thunderstorm. So it's all-weather capability. And nowadays you can get something like daily 10,000 profile per day, and these profiles are similar to like radio sound profile. So this is a very advanced technique, and nowadays has large impact on weather prediction system. Because other techniques like your remote sensing, like infrared sounder and imager, they are actually blind to the clouds, and they may not give the information below the cloud. But this technique can give the vital information even beneath the cloud. This is one of the example where this GPS RO, that is signal, have been assimilated in a tropical cyclone. So you can see that this is the actual tropical cyclone. And this is with the assimilation of GNSS RO, that is with the assimilation of the refractivity measurement. And this is the without assimilation, right? So you can see that this is much closer to the observation compared to this control experiment, which actually do not have the GPS RO signal. Okay. Then we have another signal like this measurement like soil moisture. Again, soil moisture is also possible to estimate from this passive remote sensing as well as active in something like 1.4 gigahertz to 10 and 6 gigahertz channel, and it is nowadays being used in the assimilation system. And there you can see that how this soil moisture actually is used to evaluate your land surface interaction. That is how your model land surface get this interaction between land surface temperature and soil moisture in the observation and the model. So you want to validate your model physics of land surface parameterization with the actual observation. So what it shows is the land surface interaction in the model is actually underestimated when compared to the actual observed interaction using the satellite observed land surface temperature and soil moisture. So if you can't actually represent your land surface interaction in your model, so you may not actually simulate this land surface processes like thunderstorm and other land surface like heat waves. Okay, so this is another a very critical parameter which should actually be used in your land surface model initialization. Nowadays is being used, but it was not actually earlier. I mean, thought of like it's important parameter for small short range prediction. But study has shown that soil moisture should be a very vital component for studying this heterogeneous when surface is heterogeneous to simulate your monsoon system as well as thunderstorm activity. Okay, this is again nowadays is available from both your GNSS reflectometry as well as microwave radiometry. The parameter is what you call is vegetation. As I told, vegetation actually is represent a boundary value problem or your boundary in your weather and climate model. So until you don't know that what kind of weather boundary is there in your, whether it's a urban or it's a agricultural land or it's a a water body, you cannot actually simulate or project your climate. Okay, and this one of the study actually shows this vegetation actually is a role to modulate even the Indian summer monsoon. For example, what it shows is the vegetation condition in winter actually has subsequent large impact on your following summer monsoon rainfall. For example, this Indo-Gangetic here, winter vegetation activity actually can modulate your summer monsoon rainfall activity. With the correlation is quite high. It's about something like 0.85, something like that. And this is again the correlation of monsoon trough and so monsoon rainfall and January vegetation property or the characteristics, a strong linkage. And then these are the trend in the vegetation or Indian region, actually how vegetation is increasing, that is agriculture practices, how they are changing in time. So this is from 2000, I think this is 2000 to 2020. This is, I think, mistake here is 2000 to 2020. So 20-year trends. So how your vegetation index, direct light, shows that agriculture activities are actually expanding, particularly if you see that December, January, and February here. And this agriculture practices actually will have large impact on your land surface interaction because of availability of the evapotranspiration and stuff like this. So all those things actually we should take into model, and that can be only taken when you update your own vegetation characteristics and land use type as well as this NDVI and leaf-free index into your model. So these variable along with the meteorological variable are also very actually important to incorporate in your weather and climate modeling scenarios. Now this is the overall now impact of the satellite observation. If you see this I have taken from I think ECMWF, where it has been shown that how these satellite observations actually are impacting your weather prediction. So this is southern hemisphere and this is northern hemisphere. So if you see you don't know if you don't use satellite, so your skill is around something like 0.6, right? And this is a forecast hour. But using the satellite observation, your skill is about something like 0.9. Okay, so that is a large difference actually. And northern hemisphere, again, differences are there, but compared to the southern hemisphere, the improvement is less. This is again basically because in northern hemisphere we have other observation like from other conventional sources. Okay. This again you see that how the forecast skill is improving for tropical cyclone. Now you have a 72-hour forecast error is much less compared to if you see something like 30 to 40 year back. Okay, so these are all again basically because due to the development of the both model improvement as well as your observational network and mainly the satellite observation coming into your assimilation system. This again individual satellite, that is which kind of sensor actually is giving more impact, what kind of observation you need. So like here it shows that you need the observation like microwave observation, infrared, and then like AMSUE, which is from micro, which can penetrate the clouds. Okay, so this again study is a very useful what we call observational sensitivity experiment, where actually you can define the sensor based upon your sensitivity experiment, like which observation will give you more impact. Like for example, in tropical condition, wind are more important than temperature. Okay? So like that, so wind observation becomes much more important. So we should launch the instrument which can provide the three-dimensional structure of the wind. Okay, so this is how this satellite observation overall impact the NWP system. And this is the what actually is still challenging is the current problem here is now we know that a lot of satellite observations are being used, but still if you see the assimilation point of view and the utilization of this observation. So this is one typical example here of cyclone Falin, where you see this cloud here. So when we have a cloud, so infrared cannot penetrate through the cloud. So we can see that there is a cloud top temperature, but below the cloud, I mean, we don't have any observation. And when we talk about this weather and weather prediction system, what we need is what is happening below the cloud. Because to initialize our numerical weather prediction system, we need the observation below the cloud, not above the cloud. Above the cloud actually is not that important, like what the process generating the cloud is actually happening below the cloud. So we don't have any observation from the infrared measurements here to actually initialize our weather prediction model. In microwave, because microwave can penetrate through the clouds, but once there is heavy precipitation, so microwave observation cannot give the information, because then there will be large, scattering in heavy precipitation. And to model this scattering, you need, very computationally very expensive radio transfer model, where you need to model the, scattering of like n-stream scattering, because you will have multiple scattering. So microwave observation, though, they can penetrate the small and thin clouds. So we get some observation like in a very thin cloud, right? But when there's a heavy dense cloud, or with a heavy precipitation, so we don't have any observation from microwave also. So that's where we are facing some problem. We don't have actually to initialize our numerical weather prediction system where active weather is happening. And if you see here, the tropical weather is mostly like, convective kind of weather. You see a small scale, like your system generate and then dissipate in a small, something 10 to 15 minutes, you will see that there is a system, and after 10 minutes, the system is gone. So you need a very high resolution observation for modeling the tropical convective system. If you see the higher latitudes, you can see that the clouds, they are forming like a wave. You can see clearly there's a wave which moves like east, right? From west, west to east. In westerly weather, and you can model these weather, I mean much better, because these are actually large scale system, and they want to find much convection here. But our Indian region, you need a very high resolution, temporal and spatial resolution observation in active weather conditions, which is again you need some way actually to derive this information when the weather is very active. For example, L band, as I told, like L band signal which can penetrate through the clouds, so is very useful. Like L band GNSS reflectometry can provide winds, or our GNSS radio occultation can provide some information. So those are the promising technique which can actually handle this kind of challenges. So this is the current state that state what we are actually trying to solve, that how to get the information in the cloudy region. So that's, I will stop here. I think I have some throat problem also. So I hope I am audible clearly.
Yes, sir. Yes, you were audible clearly. Thank you very much. It was a nice lecture. Before going to the question answer session, I would request everyone to switch on their videos so that we can take photos. I would request Dr. Polomi.
I think Rohini, sound is not coming properly from your side.
Is it not there?
Yeah, now it is.
Now it is audible.
So I would request for Dr. Polomi to please take some pictures.
So
Dr.
before that, if he closes that his slides.
Yeah. Sir, Tyagi sir. Yeah, there is problem with Randhir sir's cameras.
Everyone is please requested to switch on their
Yeah, some issues in my laptop camera. Actually, it's on, but it's not coming any. Nothing is visible, I think, in this.
Sir, will the mobile camera work?
Tyagi sir, if it's available, please switch on your camera. Atul sir, please switch on your camera. If it's
Already on.
Yes.
Atul's camera is already on. He has to log in.
Yeah, I have joined also with my mobile for the safe side.
I'm taking the pictures then. Please smile.
ताकि साहब नहीं है क्या? Yeah,
He's not here yet.
we'll see later on if he's available. Then.
Okay.
Okay.
So
Thank you, everyone. I've taken the few pictures.
now I request Dr. Atul Kumar Srivastava to please.
Okay, thank you, Rohini. So, thanks, Dr. Randhir, for such a nice informative talk on the topic satellite remote sensing and their technique for various meteorological parameters and its application. The talk is basically start with the global weather and climate model and how the quality of observations affects our ability to predict the weather and climate. Further, he also discussed the basic parameters of basic meteorological parameters like temperature, pressure, and wind for weather and climate modeling. He further discussed why do we need the remote sensing technique by showing the various major advancements in the development of satellite meteorological sensors and its applications. So apart from that, sir has also introduced about the basics of atmospheric remote sensing technique and the crucial spectral bands which are commonly used in the meteorological satellites. Further, he discussed in detail how the derived geophysical parameters like atmospheric temperature, atmospheric pressure, then winds, along with clouds and aerosols from the satellite measurement radiance by using radiative transfer equations. So I can see some of the questions in the question answer chat. So with due permission, I want to read that question, and sir, you please, I request you to please answer this question. So the first question is by Kumar. What are the advantages of CYGNSS over the scatterometry with regard to the wind estimation around the system center of a cyclone?
Yeah, actually, it's a very good question. So basically what happened is scatterometer operates around something like 13 gigahertz. That's K-band. And the wavelength actually is similar to that of the capillary waves, right? So what happened once there's a heavy rain, the signal in the K-band actually is not penetrating that rainy system. So you'll get that information basically of that rain scattering, not the actually information from the sea surface wind speed. Whereas in case of GNSS, what we call Cygnus, that is cyclone used for this reflectometry for cyclone, it's operate at 1.4 gigahertz. That wavelength is around 20 centimeter. And it can easily penetrate the rainfall, that whether it's a heavy rainfall or it's a cloud cover. So we can get the wind information even in a very extreme weather case like tropical cyclone from that this reflectometry based measurements. So that is the advantage over the scatterometry.
Thank you, sir. Thanks for your remark. So I have one or two questions. So with your permission, shall I ask?
Yes.
Okay. Actually, as we all know, the northern part of India mainly influenced by the low-level fog and hazy episodes in winter. So, by using satellite technique, remote sensing techniques, how it can be identified in the presence of cloud? The fog layer, how it can be identified in the presence of cloud?
Yeah, actually, I mean, what happened is once there is a cloud, I mean, if you say cloud and fog, I mean, fog is also low level kind of cloud generally we call. But once there is a cloud, let's say above a fog layer, I mean, fog is actually resting below the cloud. So from both, either you take a visible or infrared measurement, actually you cannot see a fog below the cloud. So what you will see the only clouds. But if it is a fog, I mean, without cloud, just is only fog. So what we can do is we can identify fog based upon this signature. Like one is the fog will actually have, I mean, larger lifetime compared to the clouds. So if you see the continuous image of let's say visible or infrared, so cloud will, the fog will be some kind of a more stationary when compared to the clouds. So that's how actually you can identify using this different signature in visible and this thing, infrared imagery.
Okay. And the next question is, can the satellite remote sensing be used to identify the cloud composition, like whether it is filled with liquid water or supercooled liquid water or ice crystals?
Yeah, nowadays, I mean, people are doing that work. Actually, that's what we call a channel called SWIR, short wave infrared, that is operate around something like 1 to 2 micron meter. So that particular channel actually can be used to study the cloud phases, that microphysics of the cloud. That's possible, yes.
Oh. Okay, thank you so much, sir. So, Rohini, over to you.
Okay. So
No other question from the audience, from the participants. Was that only one question from the participant?
yeah, actually, I think
Okay.
so both of us.
Fine.
Okay, so I request Dr. Swagata, who's from PIT Misra, and also Treasurer Sama, to please
Again, your voice is not very audible, Dr. Rohini.
I request Dr. Swagata, who is also Treasurer Sama, to give vote of thanks.
Okay, thanks a lot, Rohini, for giving me this opportunity. So, is my slide visible?
Yes.
Good evening to all. It's my distinct privilege to propose a heartfelt vote of thanks on this memorable occasion, marking the 7th lecture of our esteemed Satellite Weekly online lecture series. Today, we are treated to a captivating exploration of remote sensing of meteorological parameters and their applications by the distinguished scientist, Dr. Randhir Singh, Scientist, SG, Space Application Center, ISRO, Ahmedabad, India. Let us begin by extending our warmest congratulations and profound appreciation to Dr. Randhir Singh. His presentation was not only informative but also inspiring. Dr. Singh's vast expertise spanning meteorology, remote sensing,
Not audible. Swagata, not audible.
Yes, Swagata, you're not.
Network issue, huh?
In but internet connection is not.
Punomi, can you go ahead? Follow me. Can you go ahead? Take it ahead.
Yeah, sure. Let us begin by extending our warmest congratulations and profound appreciation to Dr. Randhir Singh. His presentation was not only informative but also inspiring. And his screen is not gone away. And I would also like to thank Dr. Rohini Bhabar, Dr. Saugata Paira, Dr. Atul Kumar Srivastava for organizing this lecture today. And I would also like to extend my heartfelt thanks towards Professor Someshwar Das, Secretary Sama, and Professor Ajit Tyagi, President Sama, and Dr. Bhatia, who is the chairman of the Satellite Meteorology Committee, for organizing these lectures, which has been really useful for all the participants from across the world. Thank you, everyone, and thank you for your patient hearing and being with us today. Thank you all.
Thank you, Punomi. So with this, we come to the end, and I'm sure this lecture will be good. So
Thank you, Romi. Thank you for this.
it was very, very informative, sir. So let's close the session.
Okay, thank you.
Thank you, everyone.
Thank you, sir.
It's already gone. He has left already, is it?
Yeah, sir.
Randhir Kumar has already logged out, is it? Okay.
Yeah.
त्यागी साहब भी नहीं है ना?
Yeah, Taggi sir is not there.
ये
But yes, yes.
ये सर आप मिस हो गए, फोटो सेशन में मिस हो गए और
कोई बात
स्पीकर भी चले गए.
नहीं, कोई बात नहीं. There is some internet issues here also. So, but I had been following. Don't worry, and I think quite wide-ranging talk by Randhir Singh covered. So
Mohan, are you there? Mohan has just joined.
Dr. Mohan said he may not be available.
So yeah, I think you missed also.
Actually, I am here, but I am busy with one program and just gave a talk, and just now I am joining on Marine Expo in another part of the Dhaka city. So that's today I was quite busy. Thank you, everyone.
Take one more screenshot.
Okay, sir.
I took one.
Yeah. Rohini, switch on your camera, please. Yeah.
Okay.
And what about BIT Mesra? There is somebody, I don't know, who is that? Is that Swagata? Or
sir.
Divya?
Yeah.
Yeah. Now you can take a screenshot. This will be the full screenshot. Missing the speaker. But anyway, his camera was not working.
Yes, sir. Took the photo.
can do a Photoshop. Get his profile photo put there.
Probably, yes, we can do that, sir. Yes, we can add.
Now I'm closing the YouTube.
Yeah.
Yeah, you can. By the way, I think next week we have no lecture, right, Swagata?
Yeah, there is no lecture.
21st, there is no lecture. The next
So
lecture is
let's wish everyone Durga Puja week, festive week, especially there in Mesra and colleagues from the Eastern India. And though it is become I think, pan-Indian and pan across the world also, people now celebrate Durga Puja and things like this. So it's a great time to rejuvenate and but only thing the background, what is happening in Gaza and Palestine, Israel is really sad.
Rahini, I don't have that power to stop that recording or live show. So I think you need to do that.
Recording and how to stop.
recording is stopped.